Welcome to our next lecture, which is covering section 7.2, properties of rational exponents. And the properties of rational exponents are identical to properties of exponents, which we already know. So I'm just going to highlight 4 of the major concepts. This first one, when I'm multiplying two things that have the same base, we have to add their exponents. So I would get a to the m plus n power. And as you guys can kind of imagine, since we're dealing with fractions and adding fractions, we're going to have to work with common denominators and kind of think back to some of our previous knowledge. Our next one, when I'm taking an exponent to a power, this is when I multiplied, so I would get a to the mn power. The third one I want to talk about is when I'm taking anything to a negative exponent. We know we cannot have a negative exponent, so I'm going to make it positive by bringing it to the other side of my fraction. So in this case, this was in the numerator, so I brought it down to the denominator. If it had been down in the denominator, I would bring it up into the numerator. Lastly, when I have the same base in a fraction, we often thought of this as battling, and what we're really doing is subtracting a to the m minus n power. Okay, so do we need to know things we learned last semester? Definitely. It's going to come into play quite a bit in this particular lesson. Let's start off with something easy. So I have 5 to the 1/2 times 5 to the 1/4. I notice that I have the same base. So since we're multiplying, I'm going to have to add those exponents together. Now, in order to add exponents, I need to get a common denominator, which in this case would be 4. So I get 5 to the 2/4 plus 1/4, which would be 5 to the 3/4 power. Now, for me, I think one of the tough things is I can't always leave stuff in terms of a rational exponent because I don't necessarily know that it's simplified. And some things to look for. First of all, if our base is a prime number and if our exponent is a normal fraction, we're normally in good shape. If we saw an improper fraction here, that would mean that my index number was smaller than the number of factors we had inside our radical, which we know we would need to take things out because we cannot have a group the size of, like, if my index number is 5, I can't have 5 of something in the radical and have it simplified. So those are just some things I need to be aware of. Now, there's actually 2 other answers I would accept. The first one would be the 4th root of 5 cubed. Okay, and that's just changing that from fractional into radical form. The third answer that I would accept would be the 4th root of 125. And where this came from, 125 is actually 5 cubed. So just be aware that all 3 of these are correct answers. And some of you might be thinking, well, if I'm not sure if this is simplified or not, why would we even use fractional exponents? And the reason being, technically, this problem is the square root of 5 times the 4th root of 5. And the problem I have here is that we cannot multiply things together if they don't have the same index number. So in order to simplify this, we would have to change it into exponential form. So there's definitely some steps that we would need to follow there in order to simplify it. Problem number 2, I have 8 to the 1/2 times 5 to the 1/3. According to order of operations, I'm going to look inside my parentheses first, and I cannot do anything with these because we do not have the same base, and I do not have the same exponent. So what I'm going to have to do is I'm going to have to square each of these terms separately. So I have 8 to the 1/2 times 2 times 5 to the 1/3 times 2. So I end up getting 8 times 5 to the 2/3 power. Now, even though this looks strange, this is a correct answer. The other answers that would be correct would be 8 times the cube root of 25 Or we could write it 8 times the quantity cube root of 5 squared. Okay, I would probably write either of these two answers if I was the person doing the homework. Number 3 is going to teach us something kind of important because this time looking inside my parentheses, once again, I do not have the same base. So I can't combine these. However, we notice these are both 4s. So I'm going to do something that's going to make our lives a little bit easier in a lot of these problems. We are really used to seeing an exponent outside a quantity and taking everything in the parentheses to that power. What I did here is I actually did the opposite, where since they were both to the 4th power, I took it out. Okay, so instead I just have 2 times 3 to the 4th. And I know that this is equivalent to our previous step. Now this is actually going to save me some time, because now I can do 2 times 3, which is 6. 4 times negative 1/4, because when I take an exponent to a power we multiply, would become negative 1. And I know 6 to the negative 1st power is 1/6. Number 4 deals with some battling here. I have 7/7 to the 1/3. I know 7 is really like 7 to the 1st power. So I'm going to have to do 7 to the 1 minus 1/3 power, which becomes 7 to the 2/3 power, or the cube root of 49. So sometimes problems will be as easy as they seem. Number 5 looks really similar, but it's not quite as easy because I cannot battle. The reason why I can't battle here is because I don't have the same base. However, I have these same exponents, so what I'm going to do here is I'm going to write this as 12/4 to the 1/3 power squared. And kind of a side note, it's just important for us to know that I cannot have a fractional exponent in our denominator. The reason being is because we know a fractional exponent is like having a radical, and we know we cannot have radicals in our denominator. So in this case, I can go ahead and do 12 divided by 4, which is 3. And then 1/3 times 2 is 2/3. So I get 3 to the 2/3 power, or the cube root of 9. Here we go with a problem that deals with adding radicals together. Now, we said in a previous lecture, I can only add radicals together if we have the same index number and the same radicand. So here, I happen to have the same index number, which is great. However, our radicand is not the same. So I'm going to have to see if I can simplify 16. So I know that's like 4 times 4, or 2 times 2 times 2 times 2. And we do have a group of 3 2's that I can take out. So I have the cube root of 2 plus, when I take this 2 out, I need to multiply it by the 4. So I get 8 cube root 2 because we had a 2 left over. Now I can add these two together and I get 9 cube root 2. I think it was a few chapters ago, we dealt with stuff like the square root of 1/3. And we square rooted the numerator and square rooted the denominator. And the problem that we found here is that we cannot have a radical in our denominator. So we multiplied by radical 3, and a lot of you guys didn't really put much thought into that. You just thought, oh, I'm going to multiply by whatever's in the denominator, which technically in a square root is true. But the reason why I multiply by the same thing is because I need a pair because my index number is 2. So in this case, I get the cube root of 3 over 3. So that's why I always multiply by the same thing to create a pair so we can take it out of the radical. Now our new information is going to look more like this, where I'm going to cube root the numerator and cube root the denominator. I know the cube root of 1 is 1. And I have the cube root of 4, and I'm going to do a factor tree, and it's 2 times 2. Now the problem is I need 3 of something to take it out, and I only have 2 2's. So looking at this, I need to go ahead and multiply by one more 2. Because I know that I need a group of 3 in order to take something out. So we can't just blindly multiply by whatever's in the denominator. We need to actually think, what are we missing? How many of our group do we need? When I multiply across now, I get the cube root of 2 over 2, because I have this group of 3 that I can take out. So cube root of 2 over 2 would be our final answer. Same idea here, the 5th root of 3 over the 5th root of 4. And there's honestly nothing I can do with 3. I know 4 is 2 times 2. And this time, my index number is 5. So right now I have 2 2's. I need 3 more. So I'm going to multiply by the 5th root of 8. The reason why I'm choosing 8 is because that is 2 times 2 times 2. That gives me a group of 5, so I can take that out. In the numerator, when I multiply, I get the 5th root of 24. Okay, moving on to some variables. Sometimes I think these freak people out, but I actually think it's easier because it's already like in factored form. So this first one, we're going to start with something easy. I know 9 is 3 times 3. X squared is like x times x. And y to the 4th is like y times y times y times y. Our index number here of 2 tells me I need to look for pairs. And I notice that I have a lot of pairs here. So I'm actually left with 3xy squared. And one thing I want us to notice, to figure out how many groups of 2 we had, with these variables, I actually took the exponent and divided by 2. 4 divided by 2 is 2. That tells me I have 2 groups of 2. If I had a remainder, that would tell me how many I would have to write inside my radical. So let's do a few more of these to make sure that we're feeling okay. What about the cube root of 27, a to the 6th, b to the 5th, c? I'm going to go step by step. The cube root of 27 is 3. Now looking at a to the 6th, how many groups of 3 do we have? Well, 3 goes into 6 2 times, so I end up with a squared. Next, I'm looking at this b. How many groups of 3 do we have in b to the 5th? Well, this means I have 5 b's, so I do have one group of 3, and then I have 2 b's that are left over. So I need to have a b squared left inside my radical. Lastly, I'm looking at c, and I don't have any groups there, so c also needs to stay inside my radical. Final problem of our lecture, same idea, except for this time, I have a 5th root. Okay, so if I'm starting with 5, there's actually nothing I can do, so I have the 5th root of 5. A to the 5th, how many groups of 5 do we have? Well, we have 1, so I'm going to write an A out in front. B to the 11th, how many groups of 5 do I have? I have 2 groups of 5, and I have 1 left over. C to the 8th, how many groups of 5 do we have? Well, we have 1 group of 5, and then I have 3 C's that are left over. So this would be my final answer. So this lecture, kind of the thing I want you guys to know is that you definitely need to put some thought into these problems. Because it's not just like we're doing the same skill over and over again. There definitely are some tougher ones on this assignment, so I would make sure to go through them all and make sure you are asking me if you need help on them.